welcome to our session about tensor networks for many-body quantum spin models. Today, we are going to see how we can use tensor network methods and in particular matrix product states to understand a variety of interacting quantum many-body models, in particular in one dimension. So the basic idea for today is that we are going to see how the degree of entanglement in the ground state and low energy excited states in one-dimensional interacting many-body models allows us to actually find a very efficient representation of these states using matrix product states. We will see how tensor networks and in particular algorithms related with matrix product states allows us to solve all these different quantum many-body Hamiltonians and in particular compute different types of observables that ultimately allows us to compute very, very large systems and probe quantum phase transitions even with classical resources. So the idea for today is the following. So we are going to mainly work with quantum spin models. And the typical quantum spin models that we have are like the Heisenberg model. So we have spin operators for site I, spin operators for site J. This is spin operators fulfill the commutation relations of typical angular momenta. And we are going to consider a system that has L sides. And in particular, we can have a system that has two sides. And if we have two sides, our basis is essentially four different vectors, up, 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 down, down, up, and down, down. We may have three different sides. And in this case, our basis is form of 8 states. And if we keep increasing the size of the system, the dimensionality of our basis grows exponentially. And this is effectively what limits us in terms of computing large quantum many-body models. The basic idea is that matrix product states allows us to effectively find a very efficient representation of our many-body ground state without actually having to store every single element of the basis. So from the practical point of view, if we want to solve a quantum many-body system, in principle, we would need to deal with an exponentially large number of states in the basis, in particular 2 to the L elements in the basis. And fundamentally, what we are going to show is that with matrix product states, we can actually store the whole expansion of our many-body wave function, namely the coefficients C, S1, S2, SL, without actually having to store the numbers, but just by storing a generator of these numbers. And this is the whole fundamental idea of matrix product states. So in short, one can think that matrix product states are like an algorithm for data compression. And in a pictorial way, you can think that this is like an algorithm for data compression that we use for image compression. So you can think that your true quantum many-body wave function is this picture on the left. So this is a high resolution wave function where we retain every single detail of the many-body wave function. But if you want to store this image with a relatively modest amount of computational resources, you may try to compress the image. And this is effectively what is depicted on the right. And you can think that this compressed version of the image, or in our case of the quantum many-body wave function, is what tensor networks actually exploit. And in practice, the tensor network has one parameter that allows us to determine how compressed this many-body wave function is. That is the one dimension that is going to be instrumental to understand all the physics of tensor networks. Okay, let us start with the very specific type of tensor network that we are going to focus on, which are called matrix product states. So the basic idea is that we can think that we want to store an arbitrary many-body wave function in the Hilbert space. And in particular, to store this quantum many-body wave function, we would need to store an exponentially large number of parameters. So for each combination of S1, S2, SL, we would actually need to store one real number, or if we have a general Hamiltonian, one complex number. The matrix product state ansatz, what it assumes is that this set of coefficients of the many-body wave function can actually be generated by proposing this type of parameterization of the many-body wave function. So we have a set of matrices that we call M1, M2, and L, and we have a different matrix for each component of the spin in each different site. And we just assume that we can actually write all the coefficients of the many-body wave function by using this product of matrices. And hence, this is the reason why this ansatz is called matrix product state. What it's very important to note here is that whereas in the set of coefficients of the many-body wave function, we have an exponentially large amount of parameters, in the matrix product state, we have a amount of parameters that grows simply linearly with the system size. And of course, it grows quadratically with the dimension of the matrices that we take. And in practice, one needs to ask the question whether if this type of parameterization is actually good. In a sense, if it allows you to actually parameterize the ground state and the other states that you may be interested in, and the answer is that it is, especially for one-dimensional systems. So from a physical point of view, it is very important to note that this type of ansatz makes an assumption on the states that it's parameterizing. And in particular, this assumption is that the states that you are parameterizing have a maximal amount of entanglement entropy. And in particular, the maximal entanglement entropy that you can have in this state is effectively the logarithm of the dimension of your matrix. The reason why this ansatz works well in one-dimensional systems is because the ground states of one-dimensional systems have a very small amount of entanglement, and in particular have an entanglement that almost is independent on the system size. Okay, we can now see how this type of ansatz actually allows us to massively speed up calculations for quantum many-body models. So here we are taking a typical Hamiltonian of a Heisenberg model. So we have just first neighbor exchange interaction between site n and site n plus 1. And we are comparing the time required to compute the ground state, both using exact diagonalization and using matrix product states. If you use exact diagonalization, the time required for the calculation scales exponentially with the system size. This is just stemming from the actual exponentially large number of basis vectors that you have to generate. And if you compute it with matrix product states, the time required to find the ground state increases roughly linearly with the system size, a little bit faster than linearly, but almost linearly. And what's important to note is that once you are above something like 14 or 16 sites, matrix product states actually allow you to compute ground states faster than exact diagonalization. Of course, if you have very small systems, exact diagonalization is faster than matrix product states. And in particular, if you just use this matrix product state ansatz to go to bigger and bigger systems, you actually see that you can go to quantum many-body models with up to 80 sites in a relatively small amount of time, on the order of seconds. And let me emphasize that if you think in terms of memory, that you would have to store the basis vectors of your many-body Hilbert space. With exact diagonalization, you cannot go above 20 in your computer, and you cannot go above 40 or 50 even in the biggest supercomputer. But with this matrix product stage, we can actually go to 50, 60, 70, 80 in a simple laptop and just in a matter of seconds. And this is effectively the power of matrix product states. They allow you to go to incredibly large quantum many-body models, even with relatively small computational resources. These matrix product states not only allow you to compute the ground state of your system, but they also allow you to tackle excited states of quantum many-body models. And in particular, you can take a Heisenberg model that has both first neighbor exchange coupling and a small magnetic field in the set direction, and you can compute both ground state and excited state. So the ground state of the system is going to be a singlet state, so a state that has spin equal to 0 in every single site. And then the first excited state is going to be a state that has some finite magnetization in different regions of the system, and you see that it forms some sort of standing wave. Then the next excited state is another state that has zero magnetization everywhere. So it is effectively invariant under time reversal symmetry. And then the next state has also a finite magnetization in different regions of the system, also forming a standing wave, and it is actually time reversal symmetric of the state number 1. So this is very similar to what we find in small spin chains. You can actually do this systematically and looking at level crossings as a function of the magnetic field. So if you start with a Heisenberg model that only has first neighbor exchange coupling and no magnetic field, then your ground state is a state that has magnetization zero everywhere. And then as you increase the magnetic field, then you go from a state that has magnetization zero everywhere to a state that has some magnetization in different regions of space to a different state, and so forth. And this is something that, of course, we can do for small systems, but with matrix product state, you can also do it for big systems on the order of 40 spins or even bigger. And you see that the same phenomenology appears. At zero magnetic field, you have zero magnetization everywhere, and then as you increase the magnetic field, you get a new ground state, and then a new ground state, and then a new ground state, and each one of these ground states has magnetization in different regions of space. Another very useful observable that we can compute with matrix product states are matrix elements between the ground state and an excited state. We can take, for example, a Heisenberg model that has first neighbor exchange coupling and a net magnetic field in the z direction and compute both the lowest energy state, namely the ground state that we are going to call state number 0, and the first excited state that we are going to call state number 1. And we can take this matrix element. So we take our ground state, spin operator in the x direction in site n, and excited state number 1. And this essentially allows us to see what is the probability of going from the ground state to the first excited state when we make an excitation in site number n. And what you actually observe is that for this spin 1/2 Heisenberg model, you effectively get one profile that looks like a particle in a box profile. So you can think that this corresponds to a spin excitation that has a maximal amplitude at the center of the chain, and that as you go towards the edge, it decays in probability. Something very interesting to consider is to change spin 1/2 in the Heisenberg model to spin 1. So if we have a spin 1/2 Heisenberg model, this excitation between the lowest energy state and the first excited state is this bulk excitation that we discussed before. If you now take a spin 1 model, so same Heisenberg model, but replacing spin 1/2 operators by spin 1 operators, the profile that you observe is actually completely different. And in particular, you now see a profile that it's minimal at the center and maximal at the edges. And as we will discuss before, this corresponds to a topological edge excitation that appears in the spin 1 model. The spin 1 Heisenberg model is a model that has fractionalization and topological order, and in particular features a bulk that has a full gap and at the same time gapless edge excitations. And effectively, what we are seeing here in this matrix element are the emergent gapless edge excitations. Something that we can also easily compute with matrix product states are, for example, expectation values when we put a small perturbation in a system. So for this, let us now consider a model for spin 1/2 spins where we have a dimerization in the exchange coupling. So instead of having a completely uniform exchange between site n and site n plus 1, now we have an exchange coupling that is strong, another one that is weak, another one that is strong, and so forth. And the interest of this model is that if you have a uniform chain, you effectively have a system that is gapless in the thermodynamic limit. And when it is gapless, this gives rise to effectively long-range correlations that form a power law. Whereas if you put a finite dimerization, then you actually open a gap in the system. And this gap essentially gives rise to short-range correlations in the ground state. And this is something that you can very easily see just by putting a local impurity in site number 0, in particular, a local magnetic impurity that acts as a local magnetic field, and see what is the response of the system everywhere else. So if you look at the uniform chain, you put your local magnetic impurity in site number 0, and then the ground state of the system responds to this impurity by creating a finite magnetization that becomes smaller and smaller and smaller as you get further away from the magnetic impurity, but it's always non-zero. And this decay is actually power law decay that goes roughly 1 over the distance. If you now put a finite dimerization in the system, you will open up a gap in the many-body spectra, And this opening of a gap gives rise to a certain correlation length, and the result is that once you put a local magnetic impurity inside number 0, then the ground state is also going to give rise to an oscillating magnetization, but this oscillating magnetization goes to 0 very quickly, and in particular, it goes exponentially fast to 0. And the distance at which this magnetization goes to 0 is roughly the correlation length of your many-body ground state. And let me emphasize that these types of calculations deal with systems that have nearly 100 spins, which is way, way bigger than what you could actually do with exact diagonalization. Today, we are going to mainly focus on one-dimensional quantum many-body models, but it's important to note that matrix product states are actually one of the most powerful methods that we currently have to solve generic quantum many-body models, including in 2 dimensions. And in particular, some of the paradigmatic 2-dimensional quantum many-body models, such as the 2-dimensional Hubbard model at finite doping, or the 2-dimensional Heisenberg model in different frustrated lattices, such as triangular lattice or Kagome lattice, can actually be solved with tensor networks, at least with the highest precision that we currently have. And in particular, these matrix product states, even though they are in principle mostly suitable for one-dimensional models, they actually give rise to very accurate solutions even in 2 dimensions. Of course, at the cost of using a very, very large one dimension. Let us now try to understand why matrix product states work, why they are so accurate for one-dimensional systems, and why they are much more expensive in 2-dimensional models. And to understand this, we need to understand something that it's called the entanglement entropy of a quantum many-body state. The entanglement entropy is essentially a measure of how much a quantum many-body state entangles 2 different subsets of our system. So let us imagine that you have a full quantum many-body state that is the state psi, and that this state psi is effectively just a tensor product of states on region A and states on region B. So you can think that this region A is a set of spins and this region B is another set of spins. Of course, not all the quantum many-body ground states can be written in this way. Only some of them are actually a tensor product of 2 states. But if this is the case, if we have a many-body state that is a tensor product of 2 independent states, we say that the system is separable, that it's not entangled. A classical state, for example, fulfills this condition. So you can think that, for example, if you take a state up-down, this by definition is up inside A, tensor product down in site B or in subsystem B. And if you take, for example, a spin in the x direction, that it's a linear combination of up and down, you can actually also, let's say, write down a state that it's spin in the x direction inside 1 and spin in the x direction inside 2 as a tensor product of these 2 states. But if you take a generic state, and for example, if you focus in a 2-dimensional, in a 2-side spin model, you can take the singlet state, so the state that has up, down, and down, up, then this state, there's no way of writing it as a tensor product of 2 independent states. And when we have this state, we effectively say that the state is entangled. It cannot be written as a tensor product of independent states. And this is effectively what distinguishes classical states from quantum states. A classical state can always be written in this form. A quantum state cannot be written in this form. So now the question is, how do we measure how entangled a state is, or how do we measure how quantum a state is? And this is something that can be done systematically using something called the entanglement entropy. So the basic idea is that you can take your many-body wave function and define the density matrix. This is the ket wave function, bra wave function. And this density matrix is defined in the whole space, so both in subsystem A and subsystem B. So it has block A, block B, and off diagonals, of course. Now, what you can do is you could trace over one of these subsystems. So you could compute the density matrix in subsystem A that is effectively taking the full density matrix and tracing over the degrees of freedom of subsystem B. And once you have this density matrix, you can define the entropy of the density matrix just with the typical definition of the entropy. So the trace of the density matrix times the logarithm of the density matrix. If you have a state that it's separable, so that it's a product state that you can write down as a tensor product of state A and state in B, then the entanglement entropy is zero by definition. So your reduced density matrix has only eigenvalues 1 and 0. And when you have eigenvalues 1 and 0, then the entropy is 0. In general, if you have a state that cannot be written in this way, you are going to get some finite value for the entropy. And in particular, if you take the singlet state that we discussed before, you will see that if you compute the reduced density matrix, you are going to find a finite entanglement entropy. Okay, let us now see how this entanglement entropy is actually useful already in terms of finding phase transitions. Let us take a relatively simple quantum many-body model, what it's called the transverse field Ising model. This is a model that in one limit has a classical solution, but as you introduce a new parameter in the system, then you go to the quantum limit. So if you look at the first part of the Hamiltonian, this is just the Ising Hamiltonian. So even though SZ are quantum mechanical operators, since you only have SZ in your Hamiltonian, you could actually think about this just as a classical model from statistical physics. When you introduce an in-plane magnetic field, namely this second term over here, then you start seeing that your ground state is no longer a classical state. So this term here effectively creates a quantum superposition between up and down states. This model actually has two limits that are very easy to understand. So if you take Bx equal to 0, then the only term that you have this one, and the ground state is purely ferromagnetic, right? So you have a conventional ferromagnet as in the classical Ising model. If you take a very, very large Bx, so Bx going towards infinity, you could drop out this term from your Hamiltonian, and the ground state that you get is effectively all the spins pointing in the x direction. So this model has a classical ground state for Bx equal to 0, a classical ground state for Bx equal to infinity. And between these two states, there's a quantum phase transition. And this quantum phase transition happens at Bx equal to 1/2. So now the question is, can we see this phase transition from the entanglement entropy? Let me say again that since these two states are classical, the entanglement entropy for these two states is going to be 0. But if at the middle you have quantum states that you do, then you are going to get some finite entanglement entropy. Okay, so then let us take this model and solve it with matrix product states. So if you look first at the entanglement entropy, what you actually observe is that for Vx equal to 0, you first have 0 entanglement entropy because your ground state is all the spins up. Then for very large Bx, you get a small entanglement entropy. If you keep increasing Bx, you will see that this curve goes slowly towards 0. And then at some point in the middle, you have a peak of the entanglement entropy. So the entanglement entropy alone is actually capable of telling you where you have phase transitions. And in particular, for this system that has 100 spins, you can actually think that we are almost in the thermodynamic limit. And in this limit, you actually see that your phase transition happens at Bx equal to 0.5. And of course, you could also see the phase transition if you look at an actual observable, like the magnetization in the z direction in your system. So when you are at Bx equal to 0, then your ground state has a finite magnetization because you have a classical Ising model. And as you increase Bx, then quantum fluctuations start increasing. And eventually at Bx equal to 0.5, you get a quantum phase transition to the state that only has magnetization in the x direction. And of course, the magnetization in the z direction is 0. And of course, the point in which the phase transition happens can only be determined if you compute very, very large systems. And in particular, if you compare the result for 100 sites with 20 sites, you actually see that the place where the phase transition seems to happen actually shifts with the system size. If you keep making the system bigger and bigger, you will see that it stays at 0.5. You can actually see how the entanglement entropy of the system changes as you change one of the parameters of the matrix product state, which was the bond dimension. So the bond dimension is effectively just the size of the matrices. The bigger the bond dimension, the bigger the matrices you consider in your matrix product state, and the smaller the bond dimension, the smaller the matrix is. For example, if you take a typical Heisenberg model with first neighbor exchange coupling, and you look at what is the entanglement entropy at different bonds in the system. So what you actually do in one bond is you cut the system in half along that bond, and you compute the entanglement entropy when you trace over the other part of the system. What you actually observe is that if you take a very small bond dimension, you get the entanglement entropy in the different bonds that, well, it oscillates in space, but it's relatively low. And as you increase the bond dimension more and more and more, you see that the entanglement entropy grows, and eventually it saturates to a value. So if you compare, for example, bond dimension equal to 8 with bond dimension equal to 20, you see that you describe roughly the same profile of the entanglement entropy. And in other words, what you actually think is that the ground states for bond dimension equal to 8 and bond dimension equal to 20, they are relatively similar, whereas they are pretty different from the one with bond dimension equal to 2. You can actually look at this systematically by taking the same Heisenberg model and looking at how the entanglement entropy at the center of the system evolves with the bond dimension. So if you first take a relatively small system with 10 spins, what you actually see is that the entanglement entropy at the center grows very quickly and then stays stationary. So you keep increasing the bond dimension, and the entanglement entropy at the center roughly remains constant. If you make your system bigger, then the same behavior appears, but the growth continues to a little bit higher values. So now the entropy actually saturates to a bigger value, but note that the value that you obtain for the entropy is not too larger in comparison with the one that you get for the small system. So we are making the system 3 times bigger, and the entanglement entropy is growing by roughly 40%, so a relatively small amount. And if you keep making the system bigger and bigger and bigger, you will see that this growth of the entanglement entropy goes every time to slightly bigger bond dimensions, and then it saturates to slightly bigger values, but in a very slow manner. It actually has a sublinear behavior with the system size. And this is effectively what allows you to compute very accurately ground states of one-dimensional quantum many-body models, the slow growth of the entanglement entropy. You can do this systematically by doing precisely what we discussed in the previous slide. So you compute the entanglement entropy at the center of the system, and you make the system bigger and bigger and bigger. And you see that there are, of course, some oscillations, but then overall there's a small growth of the entanglement entropy, but it's a relatively slow growth. And actually, this is a growth that is logarithmic with the system size, which in practice, you can even think that is system size independent for most of the systems that we are going to deal with. And again, this is the reason why we can actually describe large states or large systems with a relatively small bond dimension, simply because the entanglement entropy of the system grows very, very slowly with the system size. Okay, so let us now try to understand this a little bit more in detail. So what we are going to consider now is a very fine-tuned model, a very fine-tuned Heisenberg model. So this Heisenberg model is going to be a dimerized model. So we are going to take the limit where we have a chain, and these two sides are coupled, and then they are completely uncoupled. These two sides are completely uncoupled, and then fully coupled, and then fully uncoupled, and so forth. The many-body wave function of this system is actually relatively, let's say, easy. Is essentially a singlet state between every single dimer. So we have singlet over here, tensor product, singlet over here, and so forth. And what we can actually try to ask ourselves is, what is the entanglement entropy of this system? So what happens if we take the system, we cut it in half, and we integrate 1/2 of the system? So if you do that, you can actually see that the entanglement entropy becomes system size independent. So you can think about making 2 different partitions in the system. So first, let's say partition number A, and then partition number B. When you take partition number A, so you would write down the full density matrix of the system, and then trace over all the sites that are not in A. And when you trace over all the sites that are not in A, what you actually get is that the only contribution that you get to the reduced density matrix is from this bond that you cut over here and this bond that you cut over there. If you had taken a bigger bipartition of the system, you would actually get this very same contribution to the entanglement entropy. So when you cut over here, you get one contribution from this dimer. When you cut over here, you get another contribution from this dimer, but these dimers that are here inside, they do not contribute to the entanglement entropy because effectively you are not losing information when you integrate out what is outside. So in practice, you actually get an entanglement entropy that is independent on the partition that you take for your one-dimensional system. Let me emphasize that this is a very fine-tuned model where the entanglement entropy is completely independent. And of course, generic one-dimensional models are not going to have such, let's say, complete independence, but there's going to be a very, very small and slow dependence. But this is actually a relatively simple way to understand why the entanglement entropy grows so slowly in one dimension. We can actually play the very same game in two dimensions. So we could now think about a Heisenberg model where we also have some dimerization or tetramerization between the sides, and we choose our Heisenberg model in this way. So these sides are coupled by exchange coupling, and then this tetramer is decoupled from this tetramer, and so forth. And we could now do again the very same game as before. We could try to compute what is the entanglement entropy for two different partitions in the system. So we can take partition number A and partition B. And if we take partition A, when we take only these four sides as our subsystem and we trace over everything that is outside, what we actually get is that there are contributions to the entanglement entropy from this bond, this bond, this bond, this bond, and this bond. So in total, 8 contributions. If you take a bigger partition, now you actually have many more contributions. You have this bond and this one 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 and this one. And you can actually convince yourself that the number of bonds that you are cutting is proportional to the surface of the subsystem that you choose. So the bigger the subsystem, the bigger the surface. And what this actually means is that in 2 dimensions, if you tried to describe a ground state of a system with matrix product states, you would need to increase the bond dimension very, very quickly as you make the system bigger. Because remember, the bond dimension is what's essentially controlling how much entanglement entropy your many-body ground state can have. So if you have a many-body ground state of a big system, then that state needs to have a much bigger entanglement entropy than the small system, and that forces you to take a much bigger bond dimension. And of course, as you take a bigger bond dimension, that makes the calculations more and more expensive. Even though this seems like a relatively, let's say, challenging scaling, matrix product states are still relatively good for 2-dimensional systems. And of course, one doesn't compute infinite 2-dimensional systems, but actually cylinders. But this is the way in which it is done for 2-dimensional models. Okay, so now the basic idea is that matrix product states are essentially exploiting the different degrees of entanglement that the ground state has. So in 1-dimensional systems, the entanglement entropy is independent of the system size or almost independent of the system size, whereas in 2 dimensions, it grows with the system size. And what this actually tells us is that for 1-dimensional models, we can nearly describe any quantum many-body ground state using the matrix product state ansatz. And this is the fundamental reason why we can use tensor networks. So one way of thinking about it is that matrix product states are essentially a type of variational wave function that describes a very, very small subset of states of the many-body Hilbert space. So you can think that the matrix product state is essentially parameterizing this very, very small subset of your many-body Hilbert space, and that in 1 dimension, your ground state actually falls in this subset of the Hilbert space. So you actually don't need to have a parameterization that covers the whole many-body Hilbert space, because the state that you are interested in is actually in this region that you can parameterize very efficiently with tensor networks. In practice, matrix product states do not always work. So of course, they are going to work for the ground state of a 1-dimensional model, but if you are dealing with some phenomena that requires using states that have much higher entanglement entropy, then matrix product states are going to fail. And there are some instances where we actually get states that have a lot of entanglement entropy even in one-dimensional systems. So one of the paradigmatic cases is when one does time evolution in one-dimensional systems. So you take your ground state, you create a quench, and then you make the state evolve in time. What actually happens is that the entanglement entropy grows with time, and in particular, it grows linearly with time. So matrix product states allow you to do a time evolution of your observables with tensor networks, but up to a maximal time. And this maximal time is essentially determined by the entanglement entropy that you reach with time. Of course, if you go above one dimension, so to two-dimensional models, then matrix product states start having challenges. And in particular, you can consider that a two-dimensional many-body model is a one-dimensional many-body model that has long-range interactions. What this actually means is that even if you have a one-dimensional system, if you have two long-range interactions, then you may also have challenges with matrix product states. If you have highly excited states, or if you want to target highly excited states, then matrix product states also start having challenges because highly excited states live in a region of your Hilbert space where states no longer follow an area law. If you deal with low energy excited states, then you can still use matrix product states, but for high energy excited states, then the entanglement entropy is too large. And of course, if you look at far from equilibrium states, then matrix product states may also have challenges because, of course, far from equilibrium, you are essentially exploring the whole Hilbert space, and your matrix product state may not be able to parameterize those generic states. So in practice, you can think that matrix product states are a systematic way of parameterizing the many-body Hilbert space with different degrees of accuracy. So depending on the bond dimension that you choose, you are going to describe a small region of your Hilbert space, or a bigger one, or a bigger one, or a bigger one. And of course, if you keep increasing the bond dimension more and more and more, you could eventually cover the whole many-body Hilbert space. But of course, in that case, you would need exponentially large computational resources. And the advantage of matrix product states is that you can actually compute many different observables of interest in quantum many-body models with a relatively low bond dimension. So only focusing on a very, very tiny part of the many-body Hilbert space. We are, of course, using approximate states or approximate variational wave functions. So a very important question when we work with matrix product states is to determine how good our states are, or how good our eigenstates of the Hamiltonian are. And a very useful approach for this is by computing the energy fluctuation of the eigenstate. So let us imagine that you have a matrix product state that you believe that it's the ground state, or that it's close enough to the ground state. And you say, well, the energy of this state, or the expectation value of the Hamiltonian for this state, is E omega. And I know that my many-body Hamiltonian is diagonalizable, of course, and that it has a set of eigenstates. How do we know how close to one of the eigenstates is omega? So a simple way of doing this is by assuming that omega is your ground state plus some small contribution from an excited state. And if you are in this situation, a way of knowing how strong this contribution is by computing the fluctuation of the energy. So you compute the second moment of the Hamiltonian, so the expectation value of h squared minus the expectation value of h. If omega was a eigenstate of your Hamiltonian, this would be automatically 0. If you have a small contribution from an excited state, then what you can actually show is that the energy fluctuation tells you how strong that contamination from an excited state is, and of course, what is the energy difference between the ground state and the first excited state. So in practice, you can actually know how far from the ground state you are just by computing an expectation value that only involves your variational state, and without having to know what is the actual ground state energy. And this is something that it's very important to compute when you have matrix product states. So we can focus on a very specific example. So let us take again our Heisenberg model. with first neighbor exchange coupling. And let's look at the ground state energy and the fluctuation of the ground state energy as a function of the bond dimension. So if we take a very, very small bond dimension, what you actually see is that the ground state energy is, well, not far from what you would get in the perfect case, but it's higher. So what this actually means is that you have a state omega that has contributions from the ground state and from a first excited state. As you increase the bond dimension, then the energy becomes smaller, so you get closer and closer to the ground state. And if you look at the energy fluctuation, you actually see that the energy fluctuation goes to zero. So even without knowing what is the ideal ground state energy or the true ground state energy, just by looking at the energy fluctuation, you can see if you are far or close from your ground state. And in practice, this is something incredibly important when you want to compute observables with your ground state. If you have a state that is not exactly your ground state, some of the observables may be unphysical because they have contamination from excited state. So one actually needs to, let's say, double check that the ground state is converged enough through the energy fluctuation in order to trust what the observables give. This convergence with the bond dimension is something that is important not only for the ground state, but also for excited states. So that very same definition for the energy fluctuation also applies to excited states. And if you had a perfect excited state, then the energy fluctuation should actually be zero also. And you can, again, compute what is the eigenenergy as a function of the bond dimension and the fluctuation of the energy or the logarithm of the fluctuation of the energy as a function of the bond dimension. And what you observe is that when you compute both a ground state and excited states with tensor networks, then the ground state converges eventually to a very specific value as a function of the bond dimension. And the same happens for excited states, but as you go to higher and higher excited states, then the convergence happens at a later bond dimension. And this is effectively related with the fact that as you go to higher and higher energies, then states have higher and higher entanglement entropy, and therefore you need a higher and higher bond dimension to describe them properly. And this is, of course, something that you can actually also see from the fluctuation of the energy. So you see that the ground state fluctuation of the energy goes very quickly to zero. And the first excited state also goes very quickly to zero. But then as you go to higher and higher states, then the convergence is slower. And in particular, for the highest excited state, you actually get a fluctuation that is sizable even with the maximum bond dimension that we are showing in this plot. Something important to note also related with the entanglement entropy is that the entanglement entropy is very, very sensitive to what are the boundary conditions that we take for the one-dimensional problem. When we were dealing with exact diagonalization, boundary conditions in principle don't change the complexity too much. They just introduce one more coupling. But when we are working with tensor networks, boundary conditions actually increase your entanglement entropy a lot. And the idea is relatively simple. So if you look at this system on the left, so the case with open boundary conditions, what you actually observe is that the entanglement entropy that you are going to get is essentially the one that comes from the contribution of this bond. If you choose closed boundary conditions instead of open boundary conditions, what you actually observe is that now you will be cutting two different bonds. So you are cutting the bond over here and the bond over there. So you're going to actually have almost twice the entanglement entropy than in the case with open boundary conditions. And in practice, with matrix product states, it is usually a good idea to work with open boundary conditions. You can also deal with closed boundary conditions, but computationally, open boundary conditions is much more suitable because your ground states are going to have less entanglement entropy. And this is something that you can systematically compute explicitly. So you can look at the entanglement entropy at the center of a Heisenberg model and as a function of the length of the system, both with open boundary conditions and closed boundary conditions. And what you observe is that both with open boundary conditions and closed boundary conditions, your entanglement entropy grows relatively slowly. but it actually gives rise to almost twice the value with closed boundary conditions. So you see that with closed boundary conditions, you would actually need a higher bond dimension to describe this ground state than with open boundary conditions. And in practice, what this means in practice is that if you choose a very specific bond dimension, the ground state that you will get with closed boundary conditions is going to be less accurate than with open boundary conditions. Okay, let us now use tensor networks to look at some of the models that we were discussing in the previous lectures, in particular going towards the thermodynamic limit. So we now have a technique that allows us to compute 100 quantum spins. And at this stage, we are in a very good position to see phase transitions and phenomenology that only appears in very large systems. So we are going to mainly consider two different types of Heisenberg models. So we are going to take that we have first neighbor exchange coupling just for simplicity, so Sn plus 1. But we are going to think about having two different spins. In one case, we are going to consider spin 1/2, which is the case that we discussed give rise to a gapless quantum magnet. And in terms of excitations, it has gapless spin-ons. And the other case that we are going to consider is the spin 1 Heisenberg model. This model is a gapped quantum magnet. So it actually has a gap in the bulk of the system. But when you look at a system with open boundary conditions, what you actually observe is that topological fractional edge modes appear. So you have a chain that is only made of spin 1 systems. So it's a spin 1 Heisenberg model. You couple the spins, you compute the ground state, and the ground state actually behaves as if there were two emergent spin 1/2 at the edges, one at the left edge and another one at the right edge. This is one of the simplest cases of fractionalization. So you start with a particle that is spin 1, and the excitations of the system behave as if they were a fraction of your original particle. And in particular, this fraction is a spin 1/2. So we will see how we can actually see this phenomenology by computing observables with tensor networks. Let us start with the simplest case. So the case of spin 1/2 Heisenberg model. So this model can be solved both with small system sizes and large system sizes, and it is instructive to first focus on small system sizes. So if you take a system that only has two spins and you look at the spectra as a function of the magnetic field, what you actually observe is that you have here your singlet, here the triplet manifold, and as you apply a magnetic field, then you get a splitting due to the finite magnetization of the eigenstates. You can now go to slightly bigger systems, so to 4 systems. And when you go to a system with size 4, what you actually see is that you have many more states, and now you have many more splittings. And what it's important to note is that when you have two sides, then you see that your ground state switches once at magnetic field 1, right? So first, your ground state is spin equal to 0, and then here it switches and it becomes a spin equal to 1, whereas in L equal to 4, then you start with the spin equal to 0, then you go to spin equal to 1, and then eventually to spin equal to 2 here. So we have two switches of the ground state. You can look at these switches systematically just by plotting those states. And so when you plot those states, you can clearly see that there's a transition between two states. So from S equal to 0 to S equal to 1, from S equal to 0 to S equal to 1, to S equal to 2. And this is something that you can very easily compute with tensor networks, even for relatively large systems. So if you go, for example, to a system size 10, that is a system size that you can still compute with exact normalization, you will see that now you have several switches. So you start with 0, then 1, then 2, then 3, then 4, and then 5. And if you go now to much bigger systems, so with 30 sites, what you actually see is that you go almost continuously from 0 to the maximal value. So what this actually means is that for relatively large spin 1/2 systems, your ground state very quickly switches to another state. And let me emphasize that the operator that you have here in the Hamiltonian and that it's multiplied by the magnetic field is an operator that commutes with the whole Hamiltonian. What this actually means is that you are not changing the eigenstates of your Hamiltonian by applying magnetic field, but you are just changing the eigenenergies. And so when you change the eigenenergies, you are essentially just reordering who is the ground state and who is the excited state. And what this actually tells you is that you have a set of excited states that are very, very close to the ground state. And as you make the system bigger and bigger, you will see that this curve becomes smoother and smoother. So in practice, you have a quantum many-body state that it's gapless because you have excitations that are arbitrarily close to your ground state. We can do something similar with the spin 1 Heisenberg model. So now instead of considering s equal to 1/2, we are going to consider s equal to 1. And what we are going to do here is we are going to apply a relatively small magnetic field, so something on the order of 0.05. When you do that and you just look at the magnetization in real space, what you actually observe is that the magnetization is strongly localized on the two corners of the system, on the two edges of the system. So you have magnetization on the left and you have magnetization on the right. And if you sum up all these values, what you actually see is that the magnetization that you have on the left is exactly minus 0.5, and the magnetization that you have on the right is also 0.5. So this magnetization effectively belongs to an emergent spin 1/2 excitation in the model. And with tensor networks, you can actually go to bigger systems. So you could compare a system with 50 sites. That is the one that I showed you before. And you see that in the system with 50 sites, you get this magnetization on the left, this magnetization on the right, but it seems that it still lives a little bit in the center. But then when you go to bigger systems like 100 spin 1s, you see that your spin 1/2 excitation is well localized on the left edge. And then you have another excitation that is well localized on the right. So in the thermodynamic limit, you essentially get that the spin 1 Heisenberg model has a spin 1/2 excitation on the left and a spin 1/2 excitation on the right. And in the bulk, there's nothing. And you can actually show that if you increase a little bit the magnetic field, the bulk doesn't develop magnetization until a finite value, even in the thermodynamic limit. And what this tells you is that your system has a full gap in the bulk. A relatively easy way of knowing if a system has a gap or if it is gapless is by computing the non-local static correlator. So the non-local static correlator is effectively telling you what is the response of a system inside J if you put a perturbation inside I. So if you think about it from the Kubo point of view, this is what you would get from linear response theory to a local magnetic field inside I if you measure inside J. Now, you can actually think that gapless and gapped systems have completely different responses in terms of this non-local correlator. So if you have a gapless system, you're going to have a response that follows a power law behavior. So of course, as you go far from the perturbation, your response gets smaller, but it gets smaller in a relatively slow way. So following a 1/r behavior. Whereas if you have a gap, then your response becomes small very, very quickly, and in particular exponentially with the distance between the source and where you measure. This type of non-local correlator actually allows you to very easily see that the dimerized Heisenberg model, that was one of the models that had a many-body gap, actually has a gap if you have finite dimerization and has no gap if you don't have any dimerization. So you can, for example, compute a system with 40 spins 1/2 with no dimerization as the blue curve, or with finite dimerization, or even a bigger finite dimerization. And you can actually see that if you have a small dimerization, then the non-local correlator decays exponentially with the system size. If you have a stronger dimerization, it also decays exponentially, but even faster with the system size. Whereas if you don't have dimerization, it has a very, very slow decay, and you can actually check that this decay is a power law instead of exponential. You can play the semi game with the Heisenberg model, both with spin 1/2 and spin 1. So if you take the non-local correlator of spin 1/2, which is effectively the same as in the previous slide, you get this very, very slow decay that follows a power law. But if you now take a spin 1 Heisenberg model, where we, let's say, put two spins 1/2 on the edges just to get rid of the emergent excitations, then what you actually observe is that the non-local correlator decays very, very, very quickly. And in particular, it follows a linear behavior in the logarithm of the correlator versus distance, which effectively tells you that you have an exponential behavior. And now over here, you can very easily see why it is so important to be able to compute large system sizes. With the stack diagonalization, you could go roughly up to this point over here. So something like 15 spin 1, 16 spin 1. And if you go up to this point, you would actually think that the non-local correlator of the spin 1 is substantially bigger than for spin 1/2, right? But if you keep computing bigger and bigger systems, you actually see that the spin 1/2 model has a non-local correlator that decays very, 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 very slowly, whereas the spin 1 Heisenberg model has a non-local correlator that decays much, much faster. So only when you go to system sizes on the order of 40 or 50, you can truly see that the spin 1 model is effectively gapped, and that you have an exponential decay on the non-local correlators. And the requirement to go to these large system sizes essentially stems from the finite correlation length that you have in the spin 1. If your system is comparable to the correlation length, then you are not going to see this exponential decay, and you need to go to bigger and bigger systems in order to see that you have exponentially localized correlations. And something that can be also nicely computed with matrix product states are dynamical correlators. And in particular, you could compute the dynamical correlator of the spin 1 Heisenberg model and directly see the emergence of your fractional excitations in the Heisenberg model. So here what you are seeing is just the side correlator, the S plus, S minus side correlator. So you create an excitation in site n, and then you measure in site n. So this is the very same correlator that we described in one of our previous lectures. And this effectively allows you to see these ping excitations as a function of space and as a function of the energy. So when you have an excited state with energy omega that differs by a spin excitation from the ground state, then you get a non-zero value for the dynamical correlator. So if you look at the bulk of the system, what you actually see is that you need to pay a finite energy in order to create a spin excitation. And this finite energy is effectively the bulk gap that you have in the system. If you had considered the spin 1/2 instead of spin 1, then you would actually not have this gap in the thermodynamic limit. But now when you go towards the edges, you see that at the edge, there's a zero energy excitation. So you can create an excitation in your system without actually having to pay a finite amount of energy. And this excitation that you have at the edge is the fractional spin 1/2 excitation. And this peak over here is essentially telling you that you have a local degree of freedom that essentially gives rise to several almost degenerate ground states. So you have one spin 1/2 excitation on this edge and another spin 1/2 excitation on this other edge, and this appears directly in the dynamical correlator. And of course, if you had computed smaller systems, as we did in one of the previous lectures, then it would be actually a bit hard to see that this excitation here is truly an edge excitation. Whereas if you go to these big systems on the order of 40 spin 1s, you can very easily see that the Heisenberg model has topological order, it has a finite bulk gap, and fractional edge excitations.